All right, so this is section 3.9, which is tangent line approximations, which is weird because I feel like we just did the harder part of tangent line approximations. But I guess I thought it was easier because they made it a stepwise process. But either way, we're doing like the same thing we did last time where we wrote a tangent line to approximate the x-intercept, except for this time we're just writing the tangent line. So let's do it. And then we'll look at it on Desmos to see what the big idea is. So find the tangent line approximation of this at that point 0, comma 1. And then compare that with the y values. Interesting. So, yeah. So we're going to do that. How do you write the equation of the tangent line? You just need the slope and you need the point. So the point 0, comma 1, they already gave us that. So it's going to be x minus 0 equals y minus 1. We just need the slope. And if you know what the graph looks like, you'll know what the slope is. But we can also just find it by saying the derivative is the cosine of x. And then f prime of x is the cosine of the x value. So it's x prime of 0 is the cosine of 0, which is 1. Yeah, okay. So I had it twisted in my brain, but that's true. That is a lot more fun than I thought it was going to be. So our slope is 1. So there's our equation of the line. You see, it's actually just x equals y minus 1. Or if you want it in x-intercept form, x plus 1 equals y. That's our tangent line approximation. And the next thing they say is they want us to compare that with a table. So we'll do that, and we'll even do maybe one better by going to the graph. So let's actually save this. Hang on. Let's pause for a second. Yeah, so I just accidentally deleted all of that, but that's okay. At least we got a blank canvas now. So what did we want to do? We wanted to look at our equation. 1 plus sine of x is our equation. And we wanted to look at the equation we just made, x plus 1 equals y. And so look how that's definitely the tangent line. You can definitely see that that's tangent to the graph there. And yeah, look how they call it an approximation, because if we zoom in, even if we just zoom in like this, you're like, well, dang, they're basically the same graph. So if we needed to find 1 plus sine of x, we might as well just look at x plus 1, because they're basically the same thing. That's the idea. And they want us to look at a table of values. So we can do that kind of nicely by, if we call that f of x, and we call this g of x. Then we come in here to a table. We make a new table. And we can do a whole bunch of x values. So let's do like -1. I don't know a good way. Oh, good. Oh, good. Good Desmos. Good Desmos. Yes, 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 yes. That's what we wanted. So then we want here, we want this one to be f of x1, x1. So you see all of our values there. And then this one, g of x1. And so, yeah, we can see how right here in the middle, they're very close. Right here, close to 0, they're quite close. And they get further and further away as it goes. Of course, we see that on the graph as well, from both directions. That's pretty nice. That's very, very nice. So how did that work? Let's make something so we can use it for the next one too. So how did this equation come to be? This equation, so we chose a point. We chose an x value. So we can call that x1. We made that 0. This slope, this was the slope here. So that's f prime of x0. And then I'm going to go ahead and parenthesize this. So this is minus x0, and this is plus f of x0. Oh, not x0, 1. And then it's not f1, it's f prime. There we go. And so now this draws the tangent line like anywhere you want it to be. Yeah, it makes the tangent line approximation anywhere you want it to be of any graph. So let's go ahead and use that for the next one. Well, what is the next one actually? Maybe it's a bit of a thinker because it's getting into like the other section of this being differentials. So let y equals x squared. Find dy when x equals 1 and dx equals 0.01. Approximate this value with delta y for x equals 1 and delta x equals 0.01. What is the idea of that? Let's look at the textbook here. Because differentials, I feel like one of the things I always kind of get hand wavy over. See, they did the same thing we did there. But what are they trying to think about here? So they're thinking because f of x equals x squared, f prime of x equals 2x, and the differential dy. Right. That's what they're doing. Using delta x, 0.0, the change in y is that. I remember doing that error stuff. So what are we doing here? We're saying we've got dy over dx equals 2x from taking the derivative. And then now they're talking about with differentiables, you can sort of multiply both sides by dx to say that dy equals 2x dx, which is sort of getting us into the idea of integrals. And when we do that, they say find dy when x equals 1 and dx equals 0.01. Okay, we can do that just fine. So dy equals 2 times 1 times 0.01, which is 2 times 0.01, which is 0.02. Okay, and now they want you to compare this value with delta y for x equals 1 and delta x equals 0.01. So for that, they want us to be thinking about slope. They want us to be doing the change in y when the change in x is 0.01 and x equals 1. So I guess they're saying they want us to find like 1.01 minus 1 because the x is changing by 1. They want us to find delta y when, so they just want us to find, they don't even actually want the bottom. They don't really want the slope. They just want the difference in the y values. So f of 1.01 minus f of 1. And then compare that to dy. And I guess what they want to say is that that's going to approach 0 as those things get closer together, which makes sense. I mean, it's not going to be 0.02, but I guess it would make sense that it's pretty close to it. So what is 1.01 squared? 1 plus 0.01 squared is 1 plus 0.02. 1 times 0.01 times 2 plus 0.0001. 1.0201. That's not what they said it was in the book, was it? Oh, yeah, it is. Right. So that's the idea that those are going to get closer to each other as those two, as delta x is closer to each other, delta y is going to get closer to dy. Those two values get closer to each other. Yeah, I'm not super into that idea, to be honest. I don't think that's super important. Now, this is important. This is applicable. I remember this. So we're thinking about error because, every machine, when they make something, they make error. So you can actually, I wonder how this is going to relate to the different stats questions that happen with this. So the measured radius of a ball bearing is 0.7 inches, as shown in the figure. I don't think we need the figure, though. If the measurement is correct within 0.01 inches, estimated the propagated area in the volume of the ball bearing. So we'll check our answers here. I feel like there's two different things we could do. We could find the volume for 0.701 and find the volume for 0.7 and then just find the difference between those. We just want to estimate it too. Interesting. So maybe it's estimating because we're just using differentials. Well, let's use differentials the way that it makes sense to me to do it. So we'd start with the volume of the sphere, which I know is 4/3 pi r cubed. And then we do differentials there. So dv equals 4 pi r squared dr. Because what we know is we call like the dr the 0.01. So 0.01 times r, which is the 0.7. So 4 pi 0.7 squared times 0.01. And that's the dv. So that's our estimated error. Why is it estimated? Because we just used the tangent line instead of actually doing it. I guess that's my other question, is why is this supposed to be easier than actually plugging in the values if we have to come into the calculator anyway? So I got 0.0615. I mean, I suppose. So what happens if we actually find the area? Let's go to Desmos for that, just because that's going to be so much easier. So I want to type in v of x. V of x is 4/3 pi x cubed. So then I can type in v of 0.7 minus v of 0.701. That's 0.0061. And I just got 0.0. Well, that's concerning. Oh, right. It is just that. It is just that. Okay. So that's pretty close. And that's pretty close. Those were different, right? 606. Yeah, those are different because it's like a square root type of stuff. But yeah. So we were pretty close on that. Let's make sure that that's what they wanted us to do for the estimate. Oh, that was the last problem. That's what I calculated with the differentials. I got that one on NumWorks. 0.0657. Yeah, that rounds to that. Whoa. So we have two different types of error. Is large or small? The answer is best to give relative in terms of v. So you do dv divided by v. And then that's a percent. Okay. Interesting. All right. They didn't ask us to do that, though. All right, so yeah, that's actually, I guess that's really what we're getting into here. Is talking about, I think about this with related rates too. And that's what this next example is just showing us, that we take the derivative like this, and then honestly, we can think about this as just multiplying both sides by dx. See how that works for all of them. See how you need parentheses there to make that happen. See how it's just like when you multiply, this can go on the top of the fraction. So that's really all the differentials are. And so I guess that's all they're really trying to get us to do for these next problems, is just say that dy is equal to 3 cosine of x dx. Let's check back, make sure that's the only goal. But yeah, that's the only goal. Just practice writing differentials. So here, you just do it again. So 1/2. Of course, this is the square root, so that means it's going to be like this. And then you're going to multiply by the derivative on the inside, and then times the dx on the outside. And again, that's all they're going for. Oh, right, I forgot the 2's. Oh, well, the 2's canceled, so I didn't forget them. I just didn't simplify. So now use differentials to approximate 16.5. Okay, well, that's something interesting. So what's happening then? If I remember correctly, this is the idea where you're going to go that it's the square root of... Yeah, so you start, it's just the square root of x. And then when we do differentials, we get dy equals 1 over 2 root x dx. And so the idea is I can say that, like, x equals 16 and dx equals 0.5. So then I know that dy, and remember this is just dy, this is just the change in y. So we're going to have to go back, is 2 root 16 times 0.5, which is 1/8 times 1/2, which is 1/16. So it's, and that's just the change in y. So when x is 16, y is 4. So the answer, our approximate, is 4 plus 1/16. You could probably do this on Desmos too. I'm not going to do that right now though. So this is 65 over 16 as our approximation. Of course, you didn't see any of that because I was still looking at the error propagation problem. So you missed a lot of that, but it was easy enough. You didn't need to see it anyway. This was interesting though. You should see this. So you see how it was the square root. We were trying to approximate the square root of 16.5. And so I knew we were using the square root function. So I started with that one. And I took the differential and I used dy and dx. So that's just the derivative. And then I used a nice x value that I knew. So I nicely knew 16. And so that was my starting point. And I used the dx of 0.5 since we're trying to do 16.5. So I put that there. And that got me 1 over 16. And then I said that is dy. So that's just the change in y. So you got to start at what we knew, which was the square root of 16. And add on that 1/16. And so that should be a decent approximation. And now, risking forgetting to go back, we're going to come back to Desmos and test that out. Dang, gifted 5 subs. Thank you, whoever that anonymous viewer is. I appreciate that. So, what were we doing? Oh, right. We were just testing 4 plus 65 over 16. And we were comparing that to the square root of 16.5. Wow, that's wrong. Because it wasn't 4 plus 65 over 16. It was 65 over 16. Okay. Okay. There we go. There we go. There we go. Yeah, that's super close. That's super good. All right. And actually, that is the end of chapter 3. So that was fun. Chapter 3, talking about all the different applications of derivatives. Chapter 4, look at that. Getting into integrals right off the bat. So definitely stay tuned for that.